All right, Rolle's theorem. Rolle's theorem states that if f of x is continuous on the closed interval a to b and differentiable on the open interval a to b, then we have this if-then statement. If f of a is equal to f of b, that means at the beginning of the interval and at the end of the interval you have the same y value. Okay, so let's say we have this. Let's just look at the first quadrant. It doesn't really matter, but here's a and here's b. So we're looking at the interval a to b, and f of a is equal to f of b. And we know that the function is continuous from a to b and differentiable between a and b. Then if f of a and f of b are the same numbers, so this is f of a and it's also f of b, then there exists some number c between a and b, not equal to a, not equal to b, but between them, such that the derivative at c is equal to 0. Now visually, this means that we could restate Rolle's theorem sort of from a graphical perspective and say, all right, if the function is continuous from a to b and differentiable between a and b, if f of a equals f of b, then the graph has a horizontal tangent line somewhere between a and b. So let's think about this. We have 2 points here. We have a comma f of a and b comma f of b, and they have the same y value. Now connect the dots. Now connect the dots in such a way that we're following the rules or the parameters set by Rolle's theorem. So Rolle's theorem says the function is continuous. So no jumps, no holes. So jumps are non-removable discontinuities and holes are removable discontinuities, and also no vertical asymptotes. So continuous means there are no discontinuities. Okay, and these are the 3 types. And differentiable, meaning in addition to no holes, jumps, and asymptotes, no sharp corners. So if there's no holes, no jumps, no vertical asymptotes, and no sharp corners, if you connect these 2 dots somewhere, there has to be a horizontal tangent line. And it turns out, no matter how you connect the dots, somewhere, possibly more than one place, there is a horizontal tangent line. And that means the derivative, so there's one value of c, we'll call that c1. How I've drawn this, there are 2 places. So here's another horizontal tangent line, which means the derivative is 0. Remember, the derivative is the slope of the tangent line. So in this case, there's actually 2 places. There could be 5 places, 10 places, 1 place. There's got to be what Rolle's theorem is an existential theorem. And what existential means is it's telling you the existence of something, the existence. It doesn't tell you what it is. It doesn't say, here's how to find c, or here is this number c. No. It's saying there exists. So that's why we call it an existential theorem. There exists somewhere. Don't know where, but somewhere there is some number c, some x value, which we call c, where the graph has a horizontal tangent line, or where the derivative is equal to 0. Now you could pause this video and try to redraw this graph in different ways. There's no way to connect this dot and this dot with a continuous function that has no jumps, holes, no vertical asymptotes, and no sharp corners. Remember, the derivative is undefined at sharp corners, and we saw that earlier using one-sided limits. There's no way to connect these 2 dots, these 2 points, without creating a place on that graph that has a horizontal tangent line, or multiple places on the graph. So if we don't have these restrictions, there are ways to connect A to B without, or there is a way to draw a graph from A to B without a horizontal tangent line. And that we could have, let's say, I'll give a few examples. So let's say starting point and ending point. If you allow for jumps, then the graph could look like, let's say that. There's no horizontal tangent line to that graph. There's a sharp corner. Something like that. There's no horizontal tangent line. Or if there's a vertical asymptote, there is again no horizontal tangent line. But if you have these two criteria, continuous, so no discontinuities, and differentiable, no sharp corners, then between A and B, there has to be a place where the graph, at least one place. There could be infinitely many places if you have a horizontal line from A to B, and that's sort of the trivial case. But if this is A comma f of A and this is B comma f of B, and your graph is just a straight line, well, then every point has a horizontal tangent line. So you could have anywhere between 1 and infinity number of horizontal tangent lines between A and B. And that's what Rolle's theorem says. And now, well, not now, let's say in my next video, when I talk about the mean value theorem, in the mean value theorem, what I do is this. Get rid of this f of A equals f of B. So if the starting point and the ending point have the same y value, it's Rolle's theorem. But if we get rid of that and say f of A could be any number and f of B could be any other number, so it's a more general case, then this is called the mean value theorem. So it turns out that Rolle's theorem is a specific case of the mean value theorem. Okay, so that's it for Rolle's theorem. In my next video, I will discuss the mean value theorem.